We tend to think of stars as fairly straightforward things. Big balls of glowing gas that sit in the sky and warm the planets around them. But the universe, as usual, refused to keep things simple. It offers us everything from dim red embers that will outlive galaxies, to mighty giants burning 1,000,000 times brighter than our sun, to the remnants left behind when those giants finally blow: white dwarfs, neutron stars, and black holes. And as we discovered in earlier episodes, those so-called dead stars often turn out to be some of the most valuable real estate in the cosmos, producing cleaner power, denser environments, and far greater engineering potential than any living star could ever provide. This episode got written on a bit of a whim when my son asked me about the Christmas star, which one it is in the night sky and who live there, and in my somewhat rambling reply, I mentioned options folks have suggested over the years, which includes a nova, when a white dwarf absorbs a bunch of matter and brightens many thousand times over for a while. His reply was that probably no one would live there, and I had to stop myself, because there was actually a lot of reasons to live near white dwarfs or red giants, even novas. This episode isn't about that hypothetical star, but I thought we'd schedule it as a bonus episode right for Christmas as an extra one. My son's gift of inspiration to me, and my gift to you, as I do try to put more content up during the winter break anyway. Needless to say, when you ask the question, which stars could we live around, the answer is not limited to the friendly yellow G-class suns we're all familiar with. Folks tend to assume the near neighbors, the dimmer orange K-class or the slightly brighter F-class, might work. But in truth, we could live around nearly all of them, including the so-called dead stars, provided we bring the right mix of stubbornness, cleverness, and engineering. The galaxy is dominated by red dwarfs and their substellar cousins, the brown dwarfs, tiny furnaces that sip their fuel so efficiently that not a single one has ever died. They make up 3/4 of all stars, maybe more. The line on what a star is a bit arbitrary. This means the most common future home of humanity may be under a mostly soft infrared glow. Yet the great civilizations may gather around the supergiants instead, stars so bright and powerful that even the briefest sliver of their lifetime can support more people than entire clusters of dwarfs. And then there are the stellar remnants, white dwarfs, neutron stars, and black holes. We tend to imagine them as spent, dangerous, or useless, but as we discussed when colonizing black holes, a stellar corpse can be the perfect power plant, a place where matter drops in and energy pours out with astonishing efficiency. So today we'll take a grand tour of every major class of star, from the largest and shortest lived to the smallest and most enduring, and explore what life or civilization might look like around each, and in the end, we will rank them. Not just by how friendly they are to biology, but by how promising they are for great stellar empires to come. So settle in, grab a drink and a snack, maybe one of our awesome SFIA coffee mugs, like and subscribe, and let's sail into the stars. How Stars Work, a brief guide. Before we start handing out grades, we need to understand the one rule that shapes everything stars do. Mass is destiny. With stars, mass determines brightness, lifetime, temperature, and ultimately the manner of death. Composition and metallicity matter too, but far less. A star twice the sun's mass doesn't just shine a bit brighter, it burns through its fuel dramatically faster, living only a fraction as long. Meanwhile, stars half the sun's mass burn gently and steadily, shining on for tens to hundreds of billions of years. Astronomers group stars by temperature and brightness using the familiar OBA-FGKM sequence, the popular mnemonic being "Oh boy, a fine girl kissed me," running from the hottest and most short-lived O-class blue giants down to the cool, dim red dwarf M stars. And below that sequence lurk the brown dwarfs, L, T, and Y types, not quite stars at all, but still warm, long-lived furnaces. Incidentally, those letters aren't entirely random. The first popular classification system labeled stars A, B, C, and so on based on how strong their hydrogen lines were. A hydrogen line is a specific wavelength of light that hydrogen atoms absorb or emit when their electrons jump between energy levels. Stars show stronger or weaker hydrogen lines depending on their surface temperature, because only at certain temperatures are hydrogen atoms in the right state for the electrons to absorb light efficiently. We keep the A and B type stars from that era. I'm not sure if anyone had detected a red dwarf yet when that system came into being, maybe a Barnard star, but M in their case refers to stars being too cool for hydrogen lines and instead having spectrum dominated by molecules like titanium oxide, not ionized atoms. The O types, the biggest, brightest, and rarest of stars, though also the easiest to see, were originally added as a miscellaneous category. Ignoring O and M on either side of the list, everything runs in alphabetical order in decreasing temperature, except A and B being backwards, and that's because the hydrogen lines grow stronger as a star heats up, but peak at the A-type temperature range. B-types are a bit weaker and hotter, and O-types behave differently again. We now follow each letter with numbers 0 through 9, with 0 being the hottest for that class and 9 the coldest. An O0 star would be the hottest, while an M9 would be the coolest. C, D, and E got folded into the system afterward. Old E-type is now in the A-type star, whereas C actually indicated carbon-dominated spectra or late G, K, and M giants, and C and D got reused for carbon stars and white dwarfs or degenerate stars. Those colors are a bit arbitrary too. Our Sun, whose peak emission is actually blue-green, is called a yellow dwarf, a G2, even though it's brighter than 95% of stars, because the brighter and rarer stars are easier to see, and that includes giants over main sequence stars. In truth, every star is a white light source, they just vary in which colors are strongest, and even a dim red dwarf doesn't really look red. They are close to the warm glow of an incandescent bulb. My usual studio lighting here tends to correspond to cooler K-type to hotter M-type lighting. We call that warm light cool and the bluer light warm, but that's a quirk of human tradition. We associate red, yellow, and orange with warm colors of fire, and blues with coolness, even though a hot glowing object gets hotter as it shifts from red toward blue, and the same for stars. We have mega engineering tricks like star boosting or dampening for moving the spectrum of a star if it's really desired. You can hang orbital reflective statites above a star's poles to reflect the light back and heat up the light coming off the equator to hit planets, or you can wrap a tungsten shell around a very hot star to move its peak down to just under the melting point of tungsten. You need to have the shell far enough out that it doesn't melt, of course. Both tricks let you mess with the habitable zone radius of a star too, which is otherwise determined by how much light a star gives off, or rather the square root of it. How much light an object gives off is entirely based on two things: its surface area, bigger is brighter, and its temperature, which runs to the fourth power. Twice as hot means 16 times brighter, 2 to the fourth or 16. 10 times hotter would be 10,000 times brighter. There's also a shift in how much light falls in the spectrum you and I can see. Dimmer red dwarfs already give off most of their light in infrared. They also have the least surface area, most are around Jupiter size, just as most brown dwarfs are, and they are much cooler. The brightness difference between a dim red dwarf and a bright O-type supergiant can be many billions. The brown dwarf classes, L, T, and Y, were added much later, starting in the 1990s, once infrared astronomy became sensitive enough to find these faint objects. The letters don't stand for specific words or concepts, they were simply the next unused spectral letters. L dwarfs are the hottest brown dwarfs, glowing a deep red with spectral lines dominated by metal hydrides and alkali metals. T dwarfs are cooler still and defined by strong methane absorption in their spectra. Y dwarfs are the coldest of all, some barely warmer than room temperature, and their spectra are dominated by water and ammonia features. Together, these classes extend the stellar sequence in the realm of almost stars, bridging the gap between the smallest red dwarfs and giant planets. Brightness, temperature, and lifetime are not the only things that matter for habitability. The distance at which liquid water could exist on a planet, the stability of the star's output, and the size of the habitable zone all vary dramatically across star types. Big stars offer huge, bright, habitable regions, but barely give you long enough to evolve weeds, let alone civilizations. Cooler stars offer longevity measured in trillions of years, longer than the universe has existed, but pack all their warmth into an extremely tight orbital region that can make tidal locking almost unavoidable. But habitability means different things depending on what kind of civilization we're imagining. Biological evolution needs stability, moderate temperatures, and long time frames. Mega engineering civilizations, on the other hand, biological or otherwise, may care more about total energy output. A single supergiant star might power 1 trillion times more habitats than a typical red dwarf, and black holes or white dwarfs, often dismissed as dead, might prove to be some of the best engines nature ever built, as we explored before when talking about colonizing black holes and using them as cosmic utilities. So our goal today isn't simply asking, could Earth-like life evolve here, but what could a spacefaring civilization build here? What could thrive here? What empires might rise beneath the star's light? The main sequence stars, A through M. Let's begin with the stretch of the stellar family tree we know best. The main sequence, that long diagonal band on the Hertzsprung-Russell diagram, where stars spend most of their lives steadily fusing hydrogen to helium. In formal spectral notation, main sequence stars get the Roman numeral V or 5, so our Sun is a G2V or G25. This first letter tells you a star's temperature class, while the Roman numeral tells you its evolutionary stage. Class 5 means a dwarf on the main sequence. Class 4 is a subgiant just beginning to swell and cool. Class 3 marks the full red giant. Class 2 are the brighter giants above them. Class 1 refer to supergiants, and Class 0 or 1A is reserved for the ultra-rare hypergiants at the very top of the luminosity scale. So a star can be a K giant or an M supergiant, even though K and M also appear on the main sequence, because the letter indicates a temperature range. Though a G-type star, when it becomes a red giant, will be an M-type giant, going from a G2V star to maybe an M33 star. Their surfaces cool even as their brightness skyrockets, since the radius expands by factors of tens or hundreds. A red giant may be cooler in color than it once was, but with so much more surface area, it becomes vastly more luminous than it ever was during its main sequence life. Now, we'll return to O and B-type stars, but following the modern temperature sequence from hotter to cooler on the main sequence. A-type stars. A-type stars lead our tour of main sequence life, brilliant white suns radiating 5 to 50 times the luminosity of our Sun, and typically 1.5 to 3 solar masses. They burn fast and bright, living only a few hundred million years, barely long enough to finish a good geological era on Earth, let alone evolve complex life. Their brilliant ultraviolet glow makes them visually stunning, but biologically harsh. Still, their sheer luminosity opens vast real estate for megastructures. A Dyson swarm around an A-star would be almost unimaginably spacious compared to our own Sun, and the energy output would delight any Kardashev 2 civilization. A-type systems might not be cradles of life, but they are prime territory for expansion, industry, and engineered habitats. F-type stars. Dropping down in temperature brings us to F-type stars, somewhat hotter, brighter, and more energetic than the Sun, but still slow burning enough to enjoy lifespans of 2 to 5 billion years. Their luminosities fall roughly 2 to 6 times that of the Sun, with mass around 1.1 to 1.4 solar. These are bright, stable suns that give natural evolution a fair chance. They produce more ultraviolet light than G-type stars, but not ruinously so, and their wider habitable zones mean room for multiple Earth-like worlds. A civilization rising here would have ample energy and a promising but not eternal future. They are luminous enough for industry but still gentle enough for biology. They'd be great for settlement in a classic space opera sense, as they'd live billions of years still, but a key point today is that even the brightest and most short-lived stars last way longer than even the most optimistic and generous estimates of human civilization. That star will be dead in 100,000 years is honestly a very silly reason not to settle it. G-type stars. Next come G-types, our own class, and again we are on the high end at G2, and a mass and luminosity of exactly 1, since we use our Sun as the baseline, with on-average luminosities around 0.6 to 1.5 times the Sun, and lifespans of roughly 10 billion years. They sit comfortably in the middle of nearly every stellar metric. Their masses hover close to solar too, around 0.9 to 1.1 solar masses. These are presumably excellent nurseries for biology, though it's always hard to say when your sample size for habitable planets is 1. Still, G-type tend to be stable, moderate, and long-lived enough for complex ecosystems to emerge and adapt. They also shine strongly enough to support enormous megastructural civilizations, while still remaining manageable in terms of engineering demands. Even using star lifting to pull metals from stars, it's hard to source enough matter locally to englobe a star beyond simple power collection. A star 10 times brighter than our Sun needs 10 times as much matter to englobe it in the same fashion, yet it isn't even double the mass. A star 10 times as massive might be thousands of times brighter, making a Dyson much harder, as it just won't have proportionally as much matter per watt of power produced. K-type stars. Sliding even further down the sequence brings us to K-type orange dwarfs, perhaps the truest Goldilocks stars of all. Their luminosity runs from modest 0.1 to 0.6 solar, with mass around 0.6 to 0.9 solar. Their lifetimes stretch to 20 to 70 billion years or more, giving nature and civilization alike a wonderful sense of stability. Their habitable zones sit a bit closer in, but stay wide enough to avoid tidal locking trouble, and their radiation output is gentler than the Sun's. Many astrobiologists argue these stars are the best place in the universe for biology to arise and flourish. Long-lived, predictable, and well-behaved, they're also more common than G-type stars. For a civilization looking for a very long-term home, a K-type star offers a very comfortable cosmic mortgage. And again, there's also a lot more of them than G-type stars. Indeed, they outnumber all the hotter stars combined. When we rank which stars make the best homes, what we're really asking is what kind of universe we want to live in. And on Nebula, I've got a new exclusive that looks at one possible answer that humanity might not like. Rogue AI empires, when machines expand without us, where our creations inherit the stars instead. Nebula is a creator-owned streaming platform where every SFI episode comes out early and ad-free, along with my monthly exclusives, extended editions, and great series from other channels like Curious Archives, The Beautiful Horror of Deep Space, that asks who else might be living around these stars, and if it's more horrifying that they might be full of aliens, or instead, they might all be empty. Right now, Nebula is running a huge discount. With my link or the QR code on the screen, you get 50% off a yearly plan. Just $30 for a whole year, about $250 a month. And new members get a 3-day free trial, so you can check out Rogue AI for free. Head to go.nebula.tv/IsaacArthur and start watching today. M-type stars. And then we come to the great silent majority, the red dwarfs, the M-type stars, which outnumber all the other stars combined, including the orange K-types. They make up roughly 3/4 of all stars, with masses ranging from 0.08 to 0.6 solar, and luminosities as low as 1,000th of the sun's, sometimes even less. The cutoff is a bit arbitrary. Their lifetime stretches into the trillions of years, so long that not even the oldest M-type of the universe has had time to burn off more than a tiny fraction of its hydrogen. Indeed, no K-type star has gone red giant either, neither have most G-type. Only a tiny fraction of stars that have ever been born have yet died, and that term died is a bit debatable too. But back to the red dwarfs. Their habitable zones are close in, often extremely close. Planetary year lengths in the zone can be in mere weeks or even days, which predisposes planets to tidal locking and exposes them to stellar flares from the smaller, more active M stars. But for a civilization with magnetic shielding, mirrors, or megastructural shading, these challenges are manageable. And because these stars are so compact and dim, a Dyson swarm around them is far easier to build and maintain. If the Milky Way's future belongs to anyone, it may be to the civilizations of the red dwarfs, or at least for quantity of civilizations anyway. A big O or B-type star might easily house millions of times more people. B-type stars produce around 1/4 of the starlight in the galaxy, more than any other class of star, in spite of being only about 1 in 1,000 stars, with A and O each not too far behind. Most of the remainder are F and G-type, contributing about evenly, while M-types, in spite of being a supermajority of stars, only gives about 1 or 2% of the light in the galaxy. Below the true stars we find the brown dwarfs, almost stars, that never ignited sustained hydrogen fusion and whose luminosity contribution is far less than 1% of the galactic total, even if we include infrared. They really are not planets. They range from about 13 to 80 Jupiter masses, with luminosities a million times fainter than the sun, yet still radiating warmth for billions of years. L dwarfs glow in the deep red. T dwarfs show strong methane signatures. Y dwarfs are so cool they resemble hot planets. They are not stars in the strict sense and so have no V for main sequence, but they function as they dim, steady heat sources, perfect anchors for rogue habitats, infrared-adapted ecosystems, or lantern-like megastructures drifting between the stars. They may never host Earth-like biospheres, but they can host civilizations that relish stability, silence, and time. Using infrared reflective mirrors, you could bounce most of that light back down on a brown dwarf to heat the surface and make visible light come out a narrow band, extreme star boosting, but maybe more usefully such worlds have tons of fusion fuel. If you've got artificial fusion working usefully, and likely have many moons including terrestrial-sized ones, and often likely ring systems, all gold mines for spacefaring civilizations content to live inside artificially lit megastructures. Red giants. We'll move a bit faster through this section since we already have full episodes devoted to colonizing giant stars and white dwarfs, but it's important to appreciate just how much value these stars offer. Our own sun, for instance, will shine 2,000 to 3,000 times brighter at the peak of its red giant phase, and that means it could support a Dyson swarm thousands of times more energetic and populous than anything we could build today. And this isn't a fleeting moment. The sun's red giant lifetime will span on order of 1 billion years, longer than animals have existed on Earth or even in the sea. A red giant could serve as the hub of an interstellar empire of thousands of stars, while outshining most of them combined. It may also be one of the first places humanity ever colonizes outside our local neighborhood. Red giants are incredibly useful for breaking high-speed starships. Using pushing beam networks, we can accelerate starships to arbitrarily high fractions of light speed, but slowing them down is the real challenge. Big bright stars allow solar sails and tandem beam deceleration systems to work far more effectively than in dimmer systems, and red giants offer an additional trick. Their outer layers are unbelievably diffuse. The Sun's current upper atmosphere is already thinner than many vacuum chambers on Earth, and its red giant envelope will be so puffed up, especially at the edges, that a ship could literally fly through it for drag braking without burning up. Even plants can sometimes survive within a red giant's outer atmosphere for extended periods, scorched and lifeless but still intact. As a result, red giants may become the first stars humanity settles when spreading into new regions of the galaxy, natural way stations where ships can safely slow, refuel, and build outposts. When a star swells off the main sequence and becomes a red giant, its mass remains more or less the same, but everything else transforms. A star like our Sun will expand until its radius is tens or even hundreds of times larger, while its luminosity leaps upward to thousands of suns. Its surface cools to a soft orange or red glow of only a few thousand degrees, making it appear gentler despite the colossal energy pouring outward. Red giants are short-lived compared to their main sequence youth, but 1 billion years is still an eternity for civilization. Worlds that were once habitable may be roasted or swallowed, yet new opportunities emerge farther out. For prepared species, the red giant phase is less an apocalypse and more a renovation. New orbital zones open up like fresh land emerging from receding seas. The star becomes a colossal engine, powering industry and megastructures on scales far beyond what we can build around main sequence dwarfs. Red giants are perilous for the unready, but incredibly generous for those who plan ahead. Dead stars. The red giant eventually sheds its outer layers into a planetary nebula, leaving behind the hot and tiny core, a white dwarf. These stellar embryos compress roughly half a sun's mass into a sphere the size of Earth. Early in their cooling, white dwarfs may shine at 1,000th of the sun's luminosity, akin to dimmer red dwarfs, but over trillions of years they will fade to millions. Their habitable zones, if one can call them that, lie astonishingly close, only a few solar radii away. A ring world at that distance will receive a constant, gentle glow, and its orbital period will be measured in hours, nor would it need the supermaterials a Niven-scale ring world needs. Again, see that colonizing white dwarfs episode for the deep dive on some really cool megastructure options for these so-called dead stars that last longer than normal ones. Natural plants almost never survive this transition, but engineered habitats could flourish. White dwarfs are steady, long-lived, and astonishingly efficient when paired with tight-packed megastructures. Yet the main sequence stars of the childhood and adulthood of the cosmos, and red giants its flamboyant middle age, then white dwarfs are its serene elder years, quiet, enduring, and full of potential for civilizations that prize stability over spectacle. For stars originally far more massive, O and B-type stars, the giant phase ends not in a gentle shedding but in a cataclysm of a supernova, leaving behind the crushed core of a neutron star or black hole. These objects pack more than a sun's worth of matter into a sphere roughly 10 kilometers thick. Their gravity is so intense that atoms collapse and electrons merge with protons, forming neutrons. Their luminosities vary widely. Many shine dimly in visible light while others blaze in X-rays. The most famous are pulsars, neutron stars with powerful magnetic fields that sweep beams of radiation through space with clockwork-like precision. They are too hostile for natural life and too extreme for casual habitation. That does not make them useless. To a spacefaring civilization, pulsars are perfect navigational lighthouses, timing standards, and experimental platforms for high-energy physics. You could potentially use them for elemental transmutation, too. They could anchor sensor networks or communication grids. For the boldest engineers, tapping their rotational and magnetic energy could power megastructures that no ordinary star could sustain. Neutron stars are not homes, but they are tools, exquisitely precise and unimaginably powerful. That said, there are ways to settle these systems too, and their dense nature and high gravity make them almost as useful as black holes for slowing down, spaceships, and they are far more common, likely 10 times as much as black holes, though white dwarfs are even more common and also pretty good for braking. Like white dwarfs, there are tricks for making the light coming off them usable for traditional life, and of course post-biological life might find these dead stars quite appealing. Even more extreme are black holes, formed when massive stars collapse so completely that no force can stop their implosion. A stellar mass black hole typically contains 3 to 50 suns worth of mass, though larger varieties exist. On their own, black holes emit no light, but matter that spirals in them can shine brighter than entire galaxies. An accretion disk around a black hole can output tens of thousands to millions of suns of energy. For a civilization that knows how to manage these forces safely, a black hole is less a cosmic grave and more a power plant of unrivaled efficiency. Matter falling inward releases energy with astonishing returns, far greater than even nuclear fusion, and the angular momentum of the disk can be harvested in a variety of clever ways. Even isolated black holes can be used if fed matter from comets, asteroids, gas giants, or artificial fuel sources. As we discussed in earlier episodes like colonizing black holes, a black hole can become the heart of a civilization's energy grid, its waste processing system, and even its clock. They are not luminous in the conventional sense, but in civilization-scale engineering, they are the brightest candles of all. Now, before many massive stars become black holes, they pass through the spectacular and short-lived Rayet phase. These stars begin their lives with 20 or more suns worth of mass, and shed vast quantities of material through fierce stellar winds. Their luminosities can exceed hundreds of thousands of suns, and their surface temperatures soar into the tens or even hundreds of thousands of degrees. They are simultaneously the hottest and brightest stars we can observe, and amongst the shortest lived, often lasting only a few 100,000 years. We can detect them in other galaxies, so rare as they are, we can study them well due to their sheer brightness. Those stars sterilize their surroundings with intense radiation, stripping atmospheres and flooding space with energetic particles. No natural biosphere survives near them, but that does not mean an artificial habitat, shielded and with a rotating habitation drum inside it, could not do quite well there. They just need to be ready to ride those solar winds into deep space when the time for a supernova approaches. And that is a timeline on par with human civilization. For civilizations seeking raw energy or vast flows of heavy elements, Rayet stars are incredible opportunities, cosmic furnaces throwing off material that can seed future worlds. They are dangerous, unstable, and magnificent, and their presence marks regions of space destined for supernovae and black holes. Not far behind in spectacle are the O and B supergiants, the titans of stellar astronomy. These stars begin with masses 10, 20, or even 50 times greater than the Sun, and produce luminosities tens of thousands to over 1,000,000 times solar. Their lives are measured not in billions but in millions of years. They are brilliant but brief, like cosmic fireworks building toward a finale. Their ultraviolet radiation is intense, their winds can be fierce, and their environments are too harsh for life to develop, and of course too short-lived. Yet from a civilization's perspective, supergiants are extraordinary engines. Their bright output creates habitable zones so far out that entire swarms of habitats could orbit safely if built to withstand the radiation. A single supergiant could power more habitats than entire sectors of G or K-type stars. Their energy is overwhelming, but for a species that arrives prepared, supergiants offer an era, brief on cosmic scales but glorious while it lasts, of unmatched industrial potential. Across the temperature sequence are the variable stars, Cepheids, RR Lyra, flare stars, and other unstable types whose luminosities rise and fall with rhythmic precision or random violence. Their brightness variations often reflect internal pulsations or magnetic activity. These stars are poor hosts for natural habitability. Few ecosystems can endure a sun that regularly brightens or dims, but they have great scientific and engineering value. Cepheids and RR Lyra are crucial to cosmic distance measurements, serving as reliable standard candles. Flare stars may offer bursts of energy that can be harvested or modulated, and any civilization looking to leave unmistakable beacons across the galaxy could do worse than co-opting a variable star's natural rhythm. They are more instruments than homesteads, but instruments can be powerful indeed. And so we arrive at the final question: which stars would we truly want to live around? Common sense would say a good old-fashioned G-type star, but I'd argue that for long-term stability, K-dwarfs are hard to beat. They shine gently but steadily for tens of billions of years, but still have most of the benefits of a G-type, so I will rate them as a tie for best in the classic space opera planetary colonization and even Dyson swarm space habitat categories. The K-type probably should win out, especially as it has a much lower power-to-mass ratio than a G-type, and thus can far more easily afford to build a complete and substantial Dyson swarm, one full of mini habitats rather than just power collectors. For this same reason, I will give the brighter M-type red dwarfs the spot over F-type stars, and given how broad the range of M-types is, 75% of all stars, I'd put that break at 25% of solar mass range, where they go from being essentially dim or normal stars to full convective red dwarfs that will never go red giant. I put those smaller ones after the F, but before A for classic habitability, as a lot of bigger A-type stars will never have plants around them cool enough to inhabit. They are too short-lived for habitable zone plants to cool and gather oceans. But the reality is the quarter-mass and smaller red dwarfs and the bigger A-type are not good for plants anyway. They work for space habitats and post-biologicals. Bigger A and O and B-type stars are far more powerful but have the issue that they only have power. They simply don't have the mass to support giant Dyson swarms that are more than power collectors. You would likely use their immense power to starlift them to smaller size and remove their metals, expanding their lives and dimming them to something more preferable in brightness and lifetime. The O, B, and A-type stars would likely be all major hubs for civilization though, by sheer power, especially for post-biologicals, but they also need mass to make their Dyson swarms useful. I can imagine Rayet systems as large military bastions, dangerous and hard to invade, and full of doomsday weapons powered by that star. White dwarfs promise tight, elegant megastructures lasting trillions of years, while black holes provide inexhaustible energy for civilizations that can master relativistic engineering. Neutron stars and variables are tools rather than homes, yet tools that help shape the cosmic infrastructure of any advanced species. Stars that pulse in brightness can be regulated by our star boosting and dampening techniques, or they can use those bursts of power to fuel super industries like generating Kugelblitz black holes. Brown dwarfs might buy that power and in exchange serve as waypoints for bigger civilizations. Though they may be immense by our standards, home to trillions, they would seem tiny compared to even a modest K2 civilization around a K2 star, and by coincidence I would rate that as the single best kind for us to settle first, all other things being equal. The upper K range and lower G have the best options, but it's not quite a wash, and with a temperature just under 5,000 degrees, a lifetime of up to 40 billion years, and a brightness half our sun's, where Venus would be perfect in its habitable zone. Very calm stars too, and convective enough that you could starlift it and bring in new hydrogen to keep it running for trillions of years if you wanted to. Handily, Epsilon Eridani, one of our closest neighboring stars, is a K2, and often cited as an even better option for colonization than Alpha Centauri's binary, which includes a K and a G. Disagree? Tell me why in the comments below, and hit that like and subscribe button while you're there. And if you still have any money left over from holiday shopping, consider joining the channel here on YouTube or supporting us on Patreon or Subscribestar. It helps us bring you more of this content. Ultimately, there is no single best star. There are many that match a civilization's needs. Some stars offer longevity, others energy and raw power output, others opportunity. The universe is generous in its diversity, a treasure trove of different hearths, for different futures, for different kinds of people and the civilizations they will build.